not even gonna try to attempt to answer them, but we're gonna be learning some quick, interesting facts together. So they come in this box, and it says GSCE Physics Grade 9 to 1 Revision Question Cards. And learn GCSE Physics inside out with CGP. Test yourself with these cards till you know it all. Questions on the front, answers on the back. Every key topic covered. No need to bluff. CGP's cards are winners. P.S. We make cards for biology and chemistry. I think I have these two as well. So let's open it up. I already opened it, by the way. But yeah, it's empty. But I did not want to mess it up. Okay, I was just checking if there is anything else in the box. So first, I think that's the first card, yeah. And it's got some details, just a sec. I really like the way it sounds. GSCE Physics. And here it's telling us how to use these cards. So, topics match books, and the course specification is on this side of the card, which we see here. Topic 1 is about energy. Quick questions to start is this square rectangle here, and move on the harder questions, which are this one. Complete answers to each question is at the back. So they're numbered and handy tips on every card. Okay, so let's begin. Let me increase the light, turn on the light a little bit here because I can't really see very well. Okay, that's better. So first we have on the topic of energy. I don't want these to distract you, so I'm gonna leave them a little bit here. We are on the topic 1, which is energy. Number 1, energy stores and systems. So the quick questions are: number 1, name 3 different energy stores. Now let's see the answer. It's telling you could have named any 3 from the following: thermal, kinetic, gravitational, potential, elastic potential, chemical, magnetic, electrostatic, or nuclear. Okay. Number 2, give 3 ways in which energy can be transferred. Okay, let's see. Energy can be transferred mechanically. Work is done by a force. Electrically, work is done by moving charges or by is meant by a system in quotation marks. A system is an object or a group of objects. That seems like one of those questions that is so obvious that you will get wrong. Now try these. Which stores is energy transferred between when a car is slowed down by applying the brakes? Okay, number 4. Energy is transferred from the kinetic energy store of the car to the thermal energy stores of the car and the surroundings. Number 5. Describe the energy transfers that take place when water is heated in an electric kettle. Name the energy stores that are involved. Energy is transferred electrically to the thermal energy store of the kettle's heating element, which transfers energy by heating to the water's thermal energy store. Okay. Number 6. Muhammad throws a ball vertically upwards into the air. Describe and explain the energy transfers that occur from the moment the ball is released up to the highest point on its path. Assume that air resistance acts on the ball during its flight. Energy is transferred from the kinetic energy store of the ball to its gravitational potential energy store. Energy is also transferred from the ball's kinetic energy store to the thermal energy stores of the ball, and the air as work is done by air resistance to slow it down. Okay, and let's read the tip here. The ideas on this card about energy stores and transfers are super important for this whole topic, so it's a good idea to make sure that you've got your head around them before moving on. Okay, so we're done with the first card. I'm gonna leave it here and I'm gonna go turn on the light because I can't really see very well. Then let's take the second card, kinetic and potential energy stores. We've got the quick questions. When an object slows down, which stores its energy being transferred away from? When an object slows down, which stores energy being transferred away from? And the answer is the object's kinetic energy store. Number 2. A 2-kilogram block and a 5-kilogram block are both lifted to the same height. Which block has more energy in its gravitational potential energy store? And here's the answer. The 5-kilogram block has more energy in its gravitational potential energy store, which is GPE. It has a higher mass, and the amount of energy in a gravitational potential energy store depends on a mass as, and here we have the constant, which I'm not going to be reading them, or like the whole mathematical equations for it, because let's keep it to just reading. So let's go to question number 3, and also I don't want to make a mistake while reading the constants and the equations. second or miles per second. It's probably meters per second. Use a calculation to show whether or not air resistance acted on the melon as it fell. And here we have the equation. And the energy gained in the kinetic energy store is less than lost from the GP store. This means air resistance must have acted on the melon to transfer more energy to thermal stores. Okay. John stretches spring with the spring constant of 200 and I keep trying to remember what N stands for. From 117 centimeters to 127 centimeters, how much energy is transferred to the spring's elastic potential energy store? Elastic potential energy equals half times spring constant times extension to the second power. Okay, and the extension is 27 minus 17 equals 10 centimeters or 0.1 meters. Elastic energy potential equals half times spring constant times extension to the second power, which is essentially 1. Make sure you've learned the equations for the energy in an object's kinetic energy store and its gravitational potential energy store off by heart. You won't be given them in the exams. I'll make sure to learn them. Yeah, thank you. Let's go to card number 3. Yeah, I won't be reading that one for sure. Okay. Specific heat capacity. Quick questions. True or false? If a material has a high specific heat capacity, a relatively large amount of energy is required to increase its temperature by a certain amount. Is it true or false? It's true. Specific heat capacity is the energy required to raise the temperature of 1 kilo of a substance by 1 degree Celsius. What does the delta or delta symbol mean? That looks like a little triangle. The symbol delta means change in. Example, delta E or epsilon is the specific heat capacity equation. In the specific heat capacity equation is the change in the thermal energy stored. Okay. The specific, I'm just making sure the card is centered. Okay. The specific heat capacity of iron is 450 is the J joules per kilogram per degree Celsius. How much energy will have been transferred? I have to look it up. Let me just look it up, okay? Okay, it's the joule, okay? So, I'm gonna read it again. The specific heat capacity of iron is 450 joules per kilogram per degree Celsius. how much energy will have been transferred to a 0.5 kilogram iron block if its temperature rises by 10 degrees Celsius. Change in thermal energy equals mass times specific heat capacity times temperature change. And we have 2,250 joules because we have the delta, which is a change in thermal energy, and then the equation 0.5 times 450 times 10, which gives us the 2,250 joules. Now, number 4. Dan carries out an experiment to measure the specific heat capacity of tin. He uses an electric heater connected to a power supply inserted into an insulated 250-gram block of tin. Describe the energy transfers that take place during his experiment. Okay. So number 4. Work is done when a current flows. This transfers energy electrically from the power supply to the heater's thermal energy store. The energy is then transferred to the tin's thermal energy store by heating. And we have a little graph here, which is connected to the 5th question that says, the graph on the right shows Dan's results. Calculate the specific heat capacity of tin. So we see as the temperature rises, the more energy is transferred. And we've got 1,000 joules here at 20 degrees Celsius. And here we're gonna have the equation, which is taking the 200 joules per kilogram degrees Celsius gradient of graph, and then they're dividing the 20 with 1,000, and it gives us 0.02 degrees Celsius per joule. And then they're multiplying the grams. 1m. What does the m stand for? I forgot. I'm realizing I forgot most of the physics I used to know. You'll be given the specific heat capacity equation in the exam, so you don't need to learn it. You just make sure you're comfortable using it and you can arrange it to your heart's content. Okay. Let's pick up the next card, number 4. Conservation of energy. And we're still on the topic of energy. Quick questions. True or false? Oh, we have the tip here instead of the back. Okay. Energy can be created but not destroyed. And it is false. The conservation of energy principle states that energy can never be created or destroyed. That was a tricky one. 2. What does it mean if energy is transferred usefully? Let's see. Energy that is transferred usefully is transferred into the store you want it to go to. So something that you can control, basically. Almost control. Now question was asking us. Okay. Number 4. How can you sometimes tell that energy is being dissipated in an electrical device such as a mobile phone? Which of the device's energy stores is energy dissipated to? Okay. One example is the device may feel warm. Energy is dissipated to its thermal energy store. And number 5, in a closed system, what is the effect of energy transfers on the total energy of the system? Give an example of energy being transferred in a closed system. That's going to be a lengthy answer. In a closed system, energy transfers have no effect on the total energy of the system. An example of this is a cold spoon being dropped into an insulated flask containing a hot liquid. Once the flask is sealed, you can assume the liquid and spoon form a closed system. Energy is transferred by heating from the thermal energy store of the liquid to the thermal energy store of the spoon. Okay. And here we've got a little tip. I think you can read them. If a system has less energy than it started with, it can be a closed system. Some of the energy must have been transferred to the energy stores of the surroundings. Okay. Okay, and now we're getting into the topic of power. And here are some quick questions. Give the equation that gives power in terms of work and done. In terms of work done and time. Okay. Oh, okay. This is gonna be, I'm not gonna be able to read all of them. P equals watts divided by time work done. Oh. So power equals work done divided by time. So the M is best. Okay. We're gonna be learning this together, I guess. Oh, let's read this one before we read the rest. Work done is just another way of saying energy transferred. Both have units of joules, so the two equations for power are the same really. Make sure you've learned them both. What does it mean if a machine is powerful? Okay. A powerful machine is a machine that can transfer a lot of energy in a short space of time. Okay. Now try these. Okay, we've mastered the first two, so we're gonna try the rest. How much work is done by a 150 kilowatts powerboat operating at full power of for 10 seconds? I'm pretty sure that means kilowatts and kilojoules. Let's see. 1.5 mJ. B equals transfers 330 kilojoules to the thermal energy store of the heating element to bring the water to the boil. How long does it take for the water to boil? So I think we're going to be doing the same equation. So the answer is 165 seconds. P equals E divided by time. So T equals E divided by P. So we have P, which is 2 kilojoules, which is kilowatts, sorry, which is 2000 watts. So E equals 330 kilojoules, which is 330,000 joules. So time would be dividing joules by the watts. That gives us 165 seconds. And then we have another problem. Derek is entering the 100-meter lawnmower race in the speed gardening Olympiad. Imagine if this was a sport. Does this actually exist? That would be interesting. One of his lawnmowers has an engine power of 9,000 watts. On his other lawnmower has a power of 7,000 watts. The two lawnmowers are otherwise identical. Which lawnmower should he choose for the race and why? At first I thought it was a tricky question before seeing the answer. The 9,000 watts lawnmower would be a better choice for the race as it has more powerful engine. This means it can do the amount of work needed to reach the end of the course in a shorter time. Okay. A toaster takes 200 seconds to toast a slice of bread. In that time, the toaster transferred 180,000 joules of energy. What is the power of the toaster? So I think we're going to be doing the same math that we did earlier. P equals E divided by T. So then we take the joules, or the work done. Yep, the work done. 180,000 joules divided by 200, which is the seconds, and then we get 900 watts. Work done is just another way of energy transferred. I'm just rereading this. Both have units of joules, so the two equations for power are the same really. Make sure you've learned them both. Okay. Let's go to card number 6. Reducing unwanted energy transfers. First, we've got the quick questions. 1. Should thermal insulation have a high or low thermal conductivity? Let's see. Oh, that's a 3-word answer. Low thermal conductivity. Number 2. Describe how long the cooling rate of a building relates to the thickness of its walls. I'm gonna reread that again. Describe how the cooling rate of a building relates to the thickness of its walls. So, the thicker the walls of a building, the slower the building will cool. Now try these. Number 3. A lubricant is needed to the hinges of a door. Suggest an unwanted energy transfer that the lubricant reduces as the door opens and closes. wait 3 minutes, measure the final water temperature. Repeat with a beaker wrapped in different thicknesses of bubble wrap, created with different numbers of layers. The smaller the change in temperature, the better the bubble wrap is acting as an insulator. That's actually pretty smart. Number 5. State the independent, dependent, and two control variables for the experiment. Also, one question actually follows the other. Let's see. Independent variable, thickness of the bubble wrap. Dependent variable, change in water temperature. Control variables, the mass of water, the time the water cools the beaker, and lead use the bubble wrap use the initial temperature of the water. Number 6. Described how the effects of random errors could be minimized in the experiment. Okay, let's see. For some of these questions, it's like I don't want to answer them. I look forward to hearing what the answer on the back is going to be. The experiment could be repeated and a mean taken of the changes in water temperature measured for each thickness of bubble wrap. Okay, now let's read the tip. Working scientifically, questions can be a bit dull, but they tend to ask similar things. With little practice, answering them will be second nature and you'll be wishing more of them. Okay, 4 more of them. Let's go to the next card about efficiency. And we're still on the topic of energy. We've got many, I don't know if you can see, but we've got energy, then we have electricity. I used to be good with electricity. Particle model of matter. Atomic structures, I used to be good at that one too. We'll see. Forces, I wasn't very good at that. Waves, I was good. Magnetism, I was good. Space physics, I wasn't very good. So I was only good in a few of them, but I'm pretty sure I don't remember many of those. It's use it or lose it. Okay. Let's read the first quick question. What is the equation relating efficiency, total power input, and useful power output? So, the equation is efficiency equals useful power input divided by total power input. Oh, sorry. Useful power output divided by total power input. What would an efficiency of 0% tell you about the energy transfers of a device? The device doesn't transfer any energy usefully, like the question we were asked earlier. Okay. Now let's go to the harder ones. An electric motor usually transfers 24 joules of energy. The remaining 16 joules of input energy is wasted. What is the percentage of efficiency of the motor? So we have 60%. Efficiency equals useful output energy transfer divided by total input energy transfer. Total input energy transfer equals to 24 plus 16, which equals to 40 joules. Then we have useful output energy transfer equals to 24 joules. So we have the efficiency that equals to 24 divided by 40, that gives us 0.6. So as a percentage, efficiency is 0.6 times 100, and then we get 60%. Now let's go to question number 4. The total power input of the same motor is 3 watts. What is the useful power output of the motor? And it's 1.8 watts, so we do the same calculation. Efficiency equals useful power output divided by total power input. So we have 0.6 equals useful power output divided by 3. So we get useful power output, and we're gonna do the multiplication, which is 0.6 times 3, and we get 1.8 watts. Okay. Chris cycles to work on the bike. In the diagram, he wants to improve his cycling efficiency. Explain how Chris could increase his efficiency. Okay. To improve his efficiency, Chris needs to improve his useful power output by reducing the amount of energy transferred to energy stores that aren't useful. Example, he could do this by wearing a more streamlined clothes helmet, so that less work is done against air resistance as he cycles. Alternatively, he could get a better bike that is more efficient, so that less of the power he puts in when pedaling is transferred to energy stores that are not useful. He could also lubricate the moving components of his bike to reduce the amount of energy transferred due to friction. Example, to the thermal energy stores of these moving components. Okay, and now let's read the tip. The main thing to remember about efficiency is that efficiency equals useful output divided by uses of energy resources is heating name to others. Generating electricity and transport. Okay. Then we've got to question number 4. Give one way that a non-renewable energy resource can be used to heat buildings. Give another way that uses a renewable energy resource. Ways that use non-renewable energy resources include burning natural gas, burning coal, and using electric heaters which use electricity generated from non-renewable resources. Ways that use renewable resources include using a geothermal heat pump, using a solar water heater, burning biofuel, and using heaters which use electricity generated from renewable resources. Okay. Number 5. What does it mean if an energy resource is renewable? A renewable energy resource is one that will never run out as it's been or can be replenished as it is used. What does it mean? Okay, I was gonna read the same question. Briefly compare the advantages and disadvantages of renewable and non-renewable energy sources. Okay. Renewable energy resources will never run out, whereas non-renewable energy sources might. Renewable energy resources do less damage to the environment than non-renewable resources. However, renewable energy resources tend to not provide as much energy as non-renewable resources and can be less reliable as they often depend on the weather. Oh, I forgot the tape at the end. Make sure you can clearly explain the difference between renewable and non-renewable energy sources, and that you can give plenty of examples of each type and their uses. Okay. Number 9, we have the energy resources. Name. Quick questions. Name a material that can be used to make biofuels. Oops. Okay. Plant products or animal dung. Name a renewable energy resource that could be used to power a satellite in space. Solar power, tides, wind, waves are not present in space. Okay. So only solar can be used in space. Number 3. Geothermal energy can be used to heat water. State the energy stores that energy is transferred from and to when harnessing geothermal energy. From to when harnessing geothermal energy. I misread that. Okay. Let's see. Energy is transferred from the thermal energy stores of underground rocks to the thermal energy store of the water being heated. they may not be a reliable resource in the future. I think all of us know the answer to this one. Maybe, I don't know. Fossil fuels are reliable at the moment because they can be extracted from the earth at a fast enough rate. The power plants always have fuel in stock to meet demand. However, they are slowly running out, so in the future they will be harder to obtain, and there will come to a point when supply will not be able to meet demand. Okay, 7. Give an advantage and disadvantage of using nuclear power compared to fossil fuels. Nuclear power is more environmentally friendly, as like fossil fuels, it doesn't directly emit sulfur dioxide or greenhouse gases. However, the nuclear waste produced is dangerous and difficult to dispose of. There is also the risk of a major nuclear catastrophe. Okay, and let's read the tip. Each energy resource will have its own pros and cons. These are often about reliability and environmental impact. Make sure you can remember the ins and outs for each resource. Okay. And let's go to number 10. This is more on energy and resources. More on energy and resources. So let's read the quick questions. What type of energy resource only produces power during the daytime? What type of energy resource only produces power during the daytime? And it is solar power. Solar power. Okay. Then we have, what is tidal energy used for? What is tidal energy used for? And to generate electricity. To generate electricity. Okay. Number 3. Is wave power a reliable resource? If yes or no, why? 3. No. It's fairly unreliable because the waves tend to die out when the wind drops. So you will need to have constant wind for it to be reliable. Number 4. Describe how fossil fuels contribute to global warming. Number 4. Okay. Fossil fuels emit carbon dioxide and other greenhouse gases into the atmosphere when they're burned. This adds to the greenhouse effect and contributes to global warming. Okay. Number 5. How do fossil fuels impact the environment other than through global warming? Oh. Burning coal or oil releases sulfur dioxide, which causes acid rain that is harmful to trees and soil. Coal mining also ruins landscapes, and oil spillages can affect mammals and birds living in and around the sea. I remember we had these questions at the Geography GSCE 2 about fossil fuels and energy, and I'm not sure they were in the exam, but I don't know how times changed. Explain why biofuels are considered a fairly reliable energy resource. So, the crops used for biofuels take a relatively short time to grow, and different States